In many problems throughout this class, we will find it useful to consider how the mass of an object is distributed throughout the object. To do this, we will define a small piece of that object and then consider the mass that's contained within that small piece. For an object in one dimension, the differential element of length is delta L, and that length contains a certain amount of mass, delta M. We could also have a linear object in the shape of an arc, or just an arbitrary path. For an object in two dimensions, we have an area element, delta A, that contains a mass, delta M. For a volume, we have a volume element, delta V, which contains a certain amount of mass. In this case, we can write the volume element, delta V, as the area, A, times this delta X. We want to relate the small length, area, or volume element to delta M, the amount of mass contained within. In one dimension, this relation is called the linear density, lambda, which is delta M over delta L. For a uniform rod of length L and total mass M, lambda is equal to M over L. In two dimensions, the area element contains an amount of mass, sigma, times delta A, where sigma has units of mass over area. Finally, in three dimensions, the volume density, rho, connects the small mass, delta M, to the volume, delta V.
So let me summarize what the steps that we've taken are to do this differential analysis. So when you're trying to analyze a continuous mass distribution, the first step is to pick some arbitrary mass element, a small but finite size mass element, somewhere in the middle of the mass distribution. You don't want to pick one of the endpoints because the endpoints are special. You want to pick an arbitrary point somewhere in the middle, and then pick a small mass element at that point, so small but finite size. Analyze the forces acting on that mass element. So write down Newton's second law, the equation of motion for that mass element. That will give you what the action is, what the forces are on that element. Then go to the limit of an infinitesimally small element. That will give you a differential equation. You can then separate the differential equation and integrate both sides to solve the differential equation. And then finally, you can apply a boundary condition, something you know about one or the other of the endpoints, and that will allow you to solve for the function of interest at any point along your distribution.